Yes. Thank you very much. Thank you, Czaslaw. And yeah, it's really nice to be back in Austria, and I would wish that we would be in more happy times. Anyways, it's great to have to give this talk. And as you were explaining, Czaslaw, I want to be a bit elementary in the beginning before then diving into more technical parts of my talk. So first of all, I want to speak about what is gauge, why do we have to deal with gauge symmetries in physics, what are they for, and then I will move on to gravity, and I will explain what are the relevant gauge symmetries in general relativity. And then I will go into the third part, which will be more technical, where I speak about the mathematical manifestation of these gauge symmetries and how they appear in various approaches of quantum gravity, such as loop quantum gravity. So let's start out very basic. So in ordinary Hamiltonian physics, everything is very clear to us. The Hamiltonian is basically a symplectic potential. The action is basically the symplectic potential minus the Hamiltonian. And we know immediately what are the observables, which are simply all possible functions on phase space. And the algebra of observables is given by the classical, is inferred from the classical Poisson brackets. However, many systems in nature are more complicated, more subtle than that, because often we don't have direct access to observable quantities altogether. Rather, the dynamics is formulated in terms of gauge, in a gauge redundant way, in terms of gauge dependent variables. And there's the current understanding, or our understanding why that is so, has to do with how systems interact and how equivalently how to break systems apart and study subsystems. So often in the mathematical description of physical systems, they are not formulated directly in terms of gauge invariant quantities. And a simple example, a simple mechanical system that satisfies this principle is the following. So just consider a cloud of n particles and study its dynamics in its rest frame under the condition that the total angular momentum vanishes. So this is the ordinary action for n particles with a kinetic term and an interaction that only depends on the distance between the individual particles. And then we add Lagrange multipliers to impose the constraints. And it's easy to see that this action is invariant under global rotations of each individual particle and translations. Observables are then all functions on phase space that are invariant under translations and rotations. In other words, all observables, or always an observable if it Poisson commutes with the generators of the symmetries, the gauge symmetries. And now you already get an idea why such gauge symmetries have to do with how systems couple together, because if you consider now two such clouds that are initially very far separated, such that the interaction can be neglected between them, and then you bring them together, then it's clear that the coupled system under this action is not, or the coupling is not achieved by writing in terms of gauge invariant observables of each individual system, but rather of gauge invariant variables of the entire coupled system. So the gauge symmetry becomes important for how to couple two such clouds together. Or equivalently, it appears whenever we start with a large system and a large such system and split it into individual subsystems. Geometrically, what happens is that the theory is formulated on a kinematical phase space, which are the P and Q's from the previous slide, and then we impose gauge constraints that tell us that all physical configurations only appear on the submanifold of the kinematical phase space of the P's and Q's. But on top of that, we are interested in observables. And observables are these quantities that Poisson commute with the constraints that are invariant under the transformations that are generated by the gauge symmetries. In other words, we are interested in functions that are constant along the gauge orbits. And that means that the physical states are represented, or each gauge orbit actually represents a physical state. And the physical phase space is then obtained by quotient space, or equivalently by gauge fixing that intersects each orbit exactly once. The constraints, in addition to that, the constraints need to satisfy an algebra, which is simply the statement that, so geometrically, this means that each gauge orbit lies within the constraints hypersurface. The simplest example for a field theory that is a gauge theory is, of course, electromagnetism, where the kinematical phase space consists of the vector potential for the electric field and the electric field itself, which are canonically conjugate in this kinematical sense. But the physical phase space is obtained by imposing the gauge condition, which says that the electric field is divergence-free. This is just Gauss's law. And gauge transformations, so these orbits, are the gauge transformations of the vector potential. Imposing a constraint removes two dimensions from the kinematical phase space, because we first go to the constraint hypersurface and then have to identify points on the orbit. And in the case of electromagnetism, this gives us 2 times 3. So these vector fields have 3 components each, minus 2 dimensions corresponding to this one constraint. And this gives 2 times 2 physical dimensions per point, which are the 2 phase space degrees of freedom for the photon field, the 2 polarizations of the photon. But what are now, so now we have an idea of what are gauge symmetries generally, but what are now the gauge symmetries of the gravitational field? Now, to speak about the gravitational field means to speak about gravity. In special relativity, we know space and time are unified. This is the lesson of special relativity, and the geometry and causal structure of space-time is encoded into the line element, the metric. Actually, do you mind if I it just keeps going down? And now, in the first line, you see the line element as seen by inertial observers, but a general observer may move along an accelerated trajectory, and for a family of such accelerated observers, the metric coefficients will be just arbitrary functions of the space-time coordinates x. And these are the components g mu nu of the metric tensor. For instance, if we transform ourselves in a constant accelerated frame, what we find is that to leading order in 1 upon c squared, the time-time component of the metric tensor picks up space dependence. And that, combined with the equivalence principle, brought Einstein to think that the gravitational degrees of freedom are encoded in all components of the metric tensor, because he inferred from the equivalence principle that to leading order in 1 upon c squared, the space-time geometry is determined by a curved metric that depends on the Newtonian gravitational potential. And the Einstein equations that tell you that the curvature is sourced by the stress energy momentum tensor of matter turn all 10 degrees of freedom, all 10 metric components into dynamical fields on space-time. However, there's a gauge redundancy. Not all of these 10 components represent physical degrees of freedom. So what are now the gauge degrees of freedom, the gauge transformations of the gravitational field? Well, the Einstein equations are invariant under change of coordinates. That means if you write down a metric in one coordinate system and now introduce a new coordinate system, then this new metric, as expressed in these new coordinates, will still solve the Einstein equations. However, the question now appears, is any such coordinate transformation also a gauge symmetry in the Hamiltonian sense? Consider, for instance, the Schwarzschild metric to make things concrete. So here you have the line element of a black hole space-time with vanishing angular momentum. T is the time coordinate, R and omega are the radial and angular coordinates. Consider now the following change of coordinates. You simply shift the time variable forward, the time coordinate forward. Is this a gauge transformation? Well, on phase space, we expect that such time transformations are generated by a Hamiltonian, by the Hamiltonian of the system. And the black hole space-time has a mass, so we better expect that the value of the Hamiltonian evaluated on such a black hole space-time just gives the energy or the mass of the black hole. In other words, the Hamiltonian does not vanish, and this is an indication that it's not a gauge symmetry, but it has a finite value if evaluated on such a geometry, which is the mass. And therefore we expect that such asymptotic time translations are not gauge transformations. More concretely, the situation is the following. Consider the gravitational field not in its entirety. So I'm not considering the gravitational degrees of freedom in all of space-time. Consider a finite region, like a cylinder in space-time. So this is a region on space times time. And now you can ask, what coordinate transformations or diffeomorphisms in a mathematical language are now gauge transformations? And what you find is the following. Diffeomorphisms or coordinate transformations of compact support within the interior of this region, they are gauge transformations. So moving from sigma 1, so sigma is a partial initial hypersurface that is locked at the boundary. Moving from sigma 0 to sigma 0 prime is an unphysical gauge transformation. It's just a change of how to organize your degrees of freedom on sigma naught. However, if you consider diffeomorphism that moves this hypersurface forward, so which is generated by a vector field that does not vanish at the boundary, then this is not a gauge transformation. This is a physical motion that moves one configuration of the gravitational field into a different gauge inequivalent configuration. And again, as I tried to explain in the last slide, there's a physical reason why it should be like that, because these large gauge transformations, they correspond to observables like angular momentum or mass, energy, center of mass, and form momentum that are observable, that are not to be regarded as gauge transformations. And there are now two grand strategies in the literature that are somewhat opposed, but also complementary, for how to now construct gravitational observables. The first approach kind of disregards this issue of large gauge transformations that transform the boundary. It follows a relational approach, and it's conceptually very natural and simple, in fact. You just say that instead of asking what is the value of the metric at a given value of the coordinates, which is unphysical because the value of the coordinates is arbitrary, because it can be made arbitrary by any change of coordinates. You introduce physical coordinates, physical frames of reference, and say and you ask yourself, what is the value of, for instance, the metric as expressed in terms of these physical coordinates once these matter fields take a certain value. Phi I are here simply physical matter fields that characterize your rods and clocks that measure the metric components. But there are physical systems like a swarm of satellites or whatever else you want to use to measure the metric tensor. The difficulty with this approach is somewhat obvious, because it is highly nonlinear. It depends not only on the metric field, but also on the choice you make for what are your physical reference frames. So this is a highly non-local approach that depends on what frames of reference you use, and that makes it somewhat difficult to implement it in practice. A different approach follows this line of reasoning. Instead of constructing such non-local observables, the idea is to anchor your observables at the boundary. And the simplest observables that you can obtain in this approach are, in fact, the angular momentum and energy, center of mass of your system, which in general relativity are charge integrals. They are surface integrals at the boundary of space-time. And the idea is that, of course, the natural choice for such regions are given by asymptotic boundaries, where you move this external boundary all the way to infinity. But there is no reason a priori to do so. The only difficulty is that once you move the boundary inside the manifold, so you really look at the finite region, then you have to carefully explain what boundary conditions you choose at this outer time-like boundary, because now energy and radiation may cross the boundary and affect what's happening inside. So you have to be careful to specify the amount of radiation, for instance, that enters your region. And in that context, it is then quite natural or practical to work with light-like boundaries, because in that case, radiation can only come either in or out, while and there's a more natural way to characterize the initial data on this outer boundary. On a time-like hypersurface, things can move in, but can also leak out, while on a light-like hypersurface, which is generated by light rays, things can only move out or in. So the characterization of data on this outer cylinder is somewhat easier in the light-like case than in the time-like case. And but now let me be more explicit and give you more of a mathematical background of what's going on. So I will now explain you for how to characterize, for how to view general relativity as a gauge theory. The basic variables in the canonical approach are not the metric but orthonormal frames, and that has to do with how to couple spinning particles to the metric tensor. If you consider ordinary matter like fluids or electromagnetic fields, then all what you need to specify to couple these fields to the metric to the gravitational field is the metric tensor G mu nu. But spinning fields couple not directly to the metric, but they couple through gravity through orthonormal frame fields. And an orthonormal frame is basically an orthonormal basis at every point in space-time that diagonalizes the metric tensor. A spinning particle, like a spinor, then couples to this to the geometry via a connection, a notion of parallel transport, which in the case of gravity is an SL2C covariant derivative. SL2C because it is the universal cover of the Lorentz group. The curvature of space-time is then encoded into the commutator of this covariant derivative, which gives the gravity analog of the magnetic field, the curvature. And just like, or very analogously as in the electromagnetic case, what now happens is that the connection, the notion of parallel transport, is the canonical conjugate variable to the gravity analog of the electric field, which are these orthonormal frames. And these are the canonical commutation relations. But again, these are the canonical commutation relations on the at the kinematical level, that is before imposing the constraints. The constraints of the theory are the generators of the gauge symmetries. And what are the relevant gauge symmetries in this formalism? Well, they are the local frame rotations, so Lorentz boosts of your orthonormal frames, in addition to coordinate transformations or diffeomorphisms. And working in the Hamiltonian formalism, they split into spatial diffeomorphisms and temporal diffeomorphisms. And the mathematical beauty in this formalism is that all constraints assume a simple polynomial structure. The Gauss law, the constraint that generates local frame rotations, is just the gravity analog of the electromagnetic Gauss law that tells you that the divergence of the electric field is 0. And in addition to that, there are the vector and scalar constraint, which are again just polynomials of the fundamental fields. B being the magnetic field, the gravity analog of curvature, and E being the momentum conjugate to the connection, which is which are these autonomal frames. And these generators, the generators of the gauge symmetries, they vanish as constraints, which means that they vanish up to boundary terms. Now the idea to quantize this phase space is to follow the Dirac procedure. So we start out with wave functions that are complex valued functionals of the configuration variable, which is the connection. And a particularly neat such functional is just the Wilson loop operator, which is the trace of the parallel transport along a closed path. And in loop gravity, the idea is to build the entire Hilbert space by successively exciting such gravitational Wilson lines out of a vacuum state that represents no spatial geometry at all, that represents just no space, no excitations of geometry. And since these loops and Wilson lines may intersect, you can construct a complete basis, and what you find is that the resulting Hilbert space is labeled by graphs colored with representations of your fundamental gauge group, and intertwiners at the nodes wherever these Wilson lines meet that represent SU2 invariant tensors. And what you then find is, since the electric field, the gravity analog of the electric field represents a geometric quantity, what you find is that geometry itself becomes quantized. In fact, areas, angles, and volumes turn out to have discrete spectra as quantum operators. And however, in such a quantum geometry, it turns out that not all possible geometric observables can be diagonalized simultaneously. So these quantum geometries are in a certain sense fuzzy. They can be pictured as discretized geometries where only some geometric observables, like some lengths or some fundamental volumes of your building blocks, are sharp, while other geometric observables, like other angles or other edge lengths, turn out to be widely spread. So in that sense, the geometry is quantum in the most obvious sense of the word, that some geometric observables are sharp and others are not. So that sounds very great and interesting. However, there are major difficulties and challenges. What is great about this approach, that it's a kind of proof of principle, that indeed quantum gravity can be thought of just as an approach for how to successively quantize geometry. And so there's the possibility that indeed quantum general relativity is about quantizing spatial geometries. However, there are issues. For instance, how do we obtain smooth spacetime geometries in the semi-classical limit? Yes?
Can I just ask one question?
Yes.
So what you just said about, say, the discrete spectrum of the area operator and so on.
Yes.
This is all probably, is this independent of how you actually construct your theory later? I mean, as I understand, you still have different choices of your, like how to quantize the action or the Hamiltonian constraint or so.
Yes, indeed.
So two different things, no? Somehow what you said is dependent regardless of how you do the other thing.
Indeed. So what you find is that the quantization of geometry is independent from the concrete realizations of the other constraints that you still have to impose. And what you can also show is that now the question is, of course, is or this these operators, these geometrical operators, do not yet access the physical degrees of freedom of the gravitational field, which are the two polarizations of the graviton. Precisely because the metric by itself is not yet a physical degree of freedom. The physical degree of freedom is obtained, characterizes the two polarizations of the graviton, let's say. But they are all in there, and indeed they what you have in, so there are yes.
More about it anyway, maybe. Because that already answered my question.
Yeah, okay. Yeah, so in fact, that is precisely the point that I'm trying to make here. So the spins and intertwiners, they are not gravitational observables. They are not what we measure, for instance, at LIGO. What we measure at LIGO are multiples of the gravitational field, the polarization of the graviton, the strength of the gravitational radiation, etc. And so the question is, how do we extract from these kinematical observables the physical degrees of freedom, physical observables out of these spin networks? And again, there are now these two possible strategies for how to do so. One, introducing material reference frames that then access the physical degrees of freedom, or, in other words, finding a way to implement the LIGO experiment in a quantum theoretical setting by quantizing the lengths of the arms of the interferometer and so forth. But that is a very challenging and difficult and would be a highly complicated task. Instead, another approach is to consider the gravitational field in a finite domain and then quantize the degrees of freedom of the gravitational field in that finite domain. And what you then find is that because the introduction of a boundary breaks your gauge symmetries, it turns some previously unphysical gauge directions on phase space into physical degrees of freedom that you can then access and possibly quantize, such as the angular momentum of the gravitational field in that domain, which is the generator of rotations that would preserve this region so a diffeomorphism of that kind. That would be an observable for the system as characterized inside for that gravitational subsystem. And then it turns out that such diffeomorphisms are generated by a gravitational observable that is, and that gravitational observable turns out to be a charge integral, a surface integral, only over a cross-section of this null cone. Just like a charge in electrodynamics is only the integral of the electric field over the boundary. In the same way, such an angular momentum operator turns out to be just a charge integral over the boundary of the region under consideration. And what happens in this loop gravity big picture is that, so you start out with a quantum state that consists of these superpositions of Wilson lines. But if you introduce a boundary, what happens is that you break these Wilson lines apart. But these Wilson lines, they live in a representation of the underlying gauge group. So what happens is that at the open end of this Wilson line, a charge is created. A charge that transforms under all the gauge symmetries, which are internal Lorentz transformations, but also diffeomorphisms that move the boundary. And since the underlying gauge group in here is just the Lorentz group, and spinors coupled to the Lorentz group, these boundary charges that are excited are just two-component spinors. And this fits very nicely geometrically into the geometry of these null surfaces, because a spinor, a two-component spinor, which I call L in this context, defines, in fact, a null vector. In the quantum mechanics notation, this is very simple to say, simply by saying that you now have to construct a 4-vector from a spinor. So you say the time component is just the expectation value of your spinor, the norm of your spinor, and the vector component is the expectation value of the Pauli matrices. And you can easily check that this defines a null vector, a light-like vector, because the norm, so the length of this spatial vector is just the norm squared of the spinor, which is the same as L0. And indeed, Lorentz transformation, now acting with the Lorentz transformation on this vector, translates into an SL2C transformation of this spinor. So by coupling quantum gravity spin network states to boundaries, you excite spinor fields at the boundary. And it turns out that these spinor fields have a nice geometric interpretation, because they are the square root, in this sense, of the light-like generators. The null directions, the light-like directions that make up these null surfaces. And now this is the picture you get from quantum theory, but you could have completely forgotten about loop quantum gravity and would have obtained the same result, or not the same result, because one is quantum, the other one is classical, but an analogous result. In fact, so what Ashtika has shown is that yes, the electric field in gravity is conjugate to a connection. But this is true at the kinematical level and only within space-time. But what happens if you introduce a boundary? Well, if you introduce a boundary, you actually have to change the action, because to make the action still functionally differentiable, you typically have to add boundary terms that are integrals over the boundary of your region. But these boundary terms, just like a boundary term adds a contribution to the action, it also adds a contribution to the symplectic structure. And what you then find, in fact, is that the symplectic, so the kinematical phase space associated to a cross-section of this light cone has two contributions, one from the bulk, one from the interior of this disk, and another one from the boundary. And this is just a classical result that you need in order to make your variational principle, your action, well-defined in a region with a light-like boundary. And what is nice is that this, the new term that pops up in the symplectic structure is exactly the classical analog of these boundary degrees of freedom that are excited once you couple spin network states to a boundary, or once you introduce boundaries in spin networks. And what you then have is that at the kinematical phase space, so at the kinematical level, the phase space consists of degrees of freedom in the interior, in the bulk, and boundary degrees of freedom. And at the kinematical level, they are all uncorrelated. But to go to the physical level, to go to the level of the physical phase space means to impose constraints. And these constraints will couple these boundary and bulk degrees of freedom. They will say that the red part is not independent from the part in the interior of the space-time, but related to it by certain constraints. What you then find is that at the boundary, you have a boundary phase space that just tells you that this classical spinor has a momentum conjugate, which I call pi. And these are just like, so this is a two-dimensional, this is a phase space C2 cross C2, where one C2 is the configuration variable, and the other one is the momentum variable, and they each transform under SL2C, under Lorentz transformations. And then you can ask, what are observables that you can construct out of these variables? And one observable is simply the area of this two-dimensional cross-section of the boundary. And this turns out to be simply the Lorentz invariant contraction of the momentum spinor and the configuration spinor. So you just take the contraction, which is a Lorentz invariant scalar, and this turns out to define an area element. And similarly, you can construct angular momentum operators that correspond to that are the generators of these rotations, which are diffeomorphisms that normally we would think of them as gauge transformations, but they are not gauge transformations because we now have a boundary, and these transformations do not vanish at the boundary but move it. so they are large gauge transformations. And yeah, so maybe let me explain you one more thing before closing is, so one big issue in loop quantum gravity has been that people were saying that, okay, you have all these nice results on discrete geometries obtained from quantizing these Ashtekar variables using Wilson loops, and then you obtain that geometry is quantized. But have you not in a way already brought in the discretization, because you work with these combinatorical structures which are by definition discrete? So isn't it surprising that you have found something discrete? And to this I can respond now with the following. In fact, the quantization, or for instance, the area of these two-dimensional cross sections of the null cone, they are the area of this two-dimensional surface can be expressed solely in terms of these boundary variables. And to quantize these boundary variables, you don't really need to use a spin network representation. You can use a more ordinary Fock representation. So the idea is that out of these spinor degrees of freedom, you can construct two pairs of harmonic oscillators, provided you introduce additional structures that you need to build harmonic oscillators. In fact, if you have P and X, so if you have a phase space with P and X, this does not yet give you creation and annihilation operators. To have creation and annihilation operators, you need something more, because P and X have different dimensions. You need a notion of frequency. So something like but now, and since these are complex variables, you also need to add them up, you need a notion of complex structure. And if you introduce these, which at the level of at this geometric level amounts to introduce unphysical fiducial area element on the null cone, in addition to a complex structure, then you can introduce these harmonic oscillators, and the area of your two-dimensional cross sections can then be expressed on physical states simply as a difference of two number operators, which then have a discrete spectrum. Notice that this is not necessarily positive definite. That is because the notion of area that I'm using here is an oriented area element, so it can be either positive or negative depending on whether this is an expanding or a contracting null hypersurface. And then you find that still using a continuous representation, you get essentially qualitatively the same result as in loop quantum gravity. In loop quantum gravity, the spectrum is slightly different. Namely, there's a square root of j times j plus 1, but this can be traced back to simply a different ordering of your fundamental operators. It's just a different operator ordering. So the semi-classical limit is the same, but this represents a different quantum operator. So let me summarize. So first of all, we were discussing the notion of gauge and why it is important in gravity. It is important in gravity because in general relativity, the relevant gauge transformations are diffeomorphisms, coordinate transformations. But not any such coordinate transformation is also a gauge transformation, because only those diffeomorphisms that do not move the boundary turn out to be gauge transformations. Those, on the other hand, those large gauge transformations that transform, those large diffeomorphisms that transform the boundary, for instance, move it forward in time, they are physical symmetries that are generated by observables, such as angular momentum, energy, center of mass, and so on. And then the question is how to quantize such observables. Normally what we do is to go to asymptotic boundaries, but the difficulty is that in a quantum setting, the limit to infinity is should be made itself within the quantum theory, not at the classical level prior to quantizing it. And this you can do, in fact, and then you find that on the null boundaries you obtain certain observables, or you obtain observables for quasi-local angular momentum, but also for the area of a cross-section. And then I explained to you that using a more conventional Fock quantization for these boundary degrees of freedom, you obtain the same, essentially the same spectrum for your observables as in the more discrete loop quantum gravity approach, without, however, using spin networks. And this is, in my opinion, a very strong result, supporting the overall consistency of the approach. Yeah, so, and I stop here.
Quasi-local observables setting, showing that they are actually quite non-local, because you have traces like Newtonian potential everywhere.
This Hungarian guy, maybe.
No, I don't know the name. And then claiming that for this reason you cannot have local algebras in quantum gravity setting, and it's not clear how to define the subsystems.
So yeah, so here the idea is that rather than starting from a big algebra of observables and then identifying within that algebra what is a gravitational subsystem, I take a step back. I start out with a Hamiltonian formalism of gravitational subsystems. And by subsystems, I mean in that context regions of space-time with the boundary, where the boundary is at finite distance, and then I want to find observables and quantize them. And some of these observables have been identified, such as the area of the cross-section or angular momentum. So the idea is somewhat reversed. So you start out, you say the starting point is already the gravitational field in a domain, and then I specify what this domain is. For instance, is the boundary an extremal surface, or a surface of constant curvature, or a null hypersurface? These would be all different choices that you can make that define what is your algebra of observables. So it's a choice that I make before even starting the Hamiltonian analysis.
Wolfgang, I see
Yes.
on the title there was this holographic principle. You mentioned something about holographic, but
So maybe here. So no, I would not say that, because so it is holographic in the sense that your that on shell, the Hamiltonian or the angular momentum generators of diffeomorphisms are just surface integrals. But this is only true classically and sharply if you impose the constraints. But the Hamiltonian on the entire phase space, on the entire kinematical phase space, still consists of a bulk and boundary term. And in addition to that, there are degrees of freedom on each, 2 degrees of freedom on every point in sigma. And data that is specified on the time-like or null boundary is free. So there is no way to evolve from sigma 0 to sigma 1 without specifying the boundary conditions on the on this vertical time-like boundary. And so for each different choice of such boundary conditions along the time-like boundary, you would get a different Hamiltonian.
So what I thought is Giddings and Donnelly.
Ah, yes.
Do you know if this works now?
Yeah, what I said would apply in that setting, because it's a setting where you're not trying to construct local observables on the full or on the full phase space of general relativity. You rather start out with the Hamiltonian description within a domain of space-time.
Maybe one final question. So typically in quantum mechanics, when I think of just, it evolves in time according to laboratory time.
Yes.
You can kind of imagine measuring observables. Like at some fixed time, you couple your system to some measurements device, and then you get a pointer that points somewhere or so, right?
Mm-hmm.
And I wonder when you construct the observables in this setting, where it seems like lots of these even gauge transformations move you forward, but in time to some extent at least. Is it clear how you would measure them, or how should I think of determining the value of those observables or so? Would you somehow couple it with some field that comes from the outside, or is there some kind of way of thinking of this?
Yes, so that's precisely the reason why these boundary observables appear once you introduce these finite boundaries. Because in order to couple the gravitational field outside to the inside, towards inside, you need access to gauge variant, to what would be gauge variant quantities without the presence of a boundary. So the appearance of these new observables at these finite boundaries, these are precisely the kind of variables that you would measure by that these are in a way the handles you need to couple the inside to the outside, even just in pure vacuum general relativity, but also if you add matter, of course.